right, we are on. Thank you. This is software testing. This is a module that will investigate some of the concepts associated with testing in a lot more detail than what we did in a previous class during software development. So this is based on some resources, and these are some of those. In fact, there is a book called The Mythical Man Month by Frederick Brooks. Frederick Brooks is a professor now at the University of North Carolina at Chapel Hill. He is, I think, in his 90s and still going strong. But he was the developer of the IBM System 360, their most successful mainframe operating system ever. So the big picture is, I want you to understand what is testing and what is not testing, and what's important with respect to testing. Now think about any project that you will do, any project being a software project that might have hardware associated with it. And oh, by the way, these notes will also be in line too, but it might be worthwhile to take a couple of thoughts or notes as we go along. Now, the other thing that we're going to take a look at is how to test. Some skills, some processes, and things like this will always be on tests, and we'll always have examples of this later on. So, for example, Frederick Brooks said that the preferred time distribution, mostly planning and testing for developing software. And this is based on some of the data that IBM developed in the 60s and 70s, specifically, how much time do you think a software developer really takes developing software? And the answer is only 17%. And in fact, that may even be less now. A lot of time is spent planning, a lot of time is spent component testing, and a lot of time is spent system testing. And the whole idea or the thought is, the sooner you start coding, the longer it's going to take to finish your entire software package. Because, and I hope we've instilled this in you before, you cannot just start writing code if you don't know what you're writing code against. What have we said that you needed? Requirements, right? And what else? Designs, high-level and low-level designs. So you need to ensure that you do lots of planning and lots of designing before you actually get into the coding. So the whole the philosophy is that for a software assignment for your labs, or a software product for a mobile phone, or anything like that, you cannot fully test a program. It is just too complex for you to be able to fully test it. And when you complete your testing, there is no way to ensure that the program does not have any bugs inside of it. And the mission of testers is not to ensure the program is complete with complete testing, but it actually is to find as many bugs as possible. And there are certain tricks that one can do to identify those bugs. So, questions. What's the point of it? What distinguishes good from bad testing? How much testing is enough, and how can you tell when you've done enough? And a lot of this is methodical, and a lot of it is experience. So let's dig in and take a look at this. There is no way you will ever do complete testing, period, because there are too many possible inputs associated with most of your software applications. There's also a lot of invalid inputs. And there's a lot of differences, especially in embedded systems, because timing is also very important with respect to your operation of the embedded system. There's too many control paths associated with these timings, data, conditional loops, interrupts, etc. Combinatorial explosion says that you cannot test all different combinations of input and timings, etc. And, oh, by the way, you would need to retest after every bug fixed. So you can't prove programs are correct using logic. So you can do other things to worry about your testing. So let's take a good example. And I did this in the other class, or I'm sorry, I did this in my other session, and it's on my laptop, so I think I'm going to have to pull it up later. I think I will do that in a few moments. So I guess I will come up with one quick little assessment, and I forgot to bring my paper in with me. So from that respect, so that we are able to see this on the video. Let's take a look at a small little problem, right? And I think I've addressed this before, haven't I? Where I say int values 100 int I. Look good so far? All right? All right. So we'll start a small little program for I equals 0, I less than and equal to 100, I plus plus, values I is equal to I. And I'm going to have other things too. So turn to your neighbor and figure out what's wrong with this code and what are the characteristics of this code. And we'll come back in a minute or two. And welcome back. By the way, I made a change. I probably should have made that known. I put the number 1 here, all right? So now, okay, question. I'm going to pick on one of you specifically, somebody I haven't seen and picked on before. The young lady right there in the grayish shirt. Have you volunteered anything? Okay. So what is your assessment on that?
The contents of the array are going to be 1.
The contents of what is going to be 1? The array, the whole array. Okay.
So it's going to be like 101 contents will be 1.
Okay. What does that mean?
Because it's 0 to 100.
Yeah. What is 101? What does that mean?
It should have been for 100 digits, like 100 contents. It should have been 0 to 99.
All right. 0 to 99. How would you? So what's wrong up there?
Nothing is wrong. The 101 content would be 1 as well.
But what's wrong with the code?
It should have been less than 100.
All right, less than 100. So what's the characteristics? How will this actually execute?
It will, the C compiler will write x of 100, value of 100 equal to 1 as well.
Okay, what does that mean? How will it run?
It will overwrite.
Yeah, but how will it run? What will happen with this code? No, there's one possibility for this code right here. This is an infinite loop. That is correct. All right? Would you all agree this is an infinite loop? How?
Oh, yes. At the values of 100, the value of I will be correct.
Well, here's the deal. This is an integer, right? Or an integer array. So the 101st location of this array is this, because it's been defined right afterwards. So as it goes through, in the 101st time through this for loop, this says values of 101 is equal to 1. Well, the location, this is a valid C instruction, and because C doesn't check the bounds on arrays, it will just put it in the next memory location right after that, which turns out to be I. And so at this point, you will assign the number 1 to the integer I. And then what will happen? Well, I is going to be equal to 2, or 1 at that time. And oh yeah, it meets this, so it'll increment it and then run it. Actually, increment it, check it, and then run it. So the answer is infinite loop. Now, here's why I bring this up. Okay, let's be honest. How many of you recognized it would be an infinite loop? At least one person, right? Right? Just one? Just 2? All right. Really? Wow. This is important with respect to testing. Because why? Well, if I were to run this code, I obviously would find an error. Now, then you have to find out what is the location of the error. So this is a good example of how do you test this? All right? So in this case, if this were one of many lines of code in the program, and if it were somewhere in the middle, I would have an infinite loop, and I really wouldn't know where the infinite loop were unless I started to step through and take a look and identify what would happen. So when you're talking about testing, you have to think about how are you going to test at what level. In other words, you could have just written a few lines of code and then tested it, or you could do what we call the Big Bang Theory and just throw everything in there and then try and start testing it. And so that's the precursor to thinking about what we're going to be doing for this, for the rest of this exercise, for the rest of this lecture. Alrighty. And again, you can't verify that the process of verifying that the program works correctly, you can't verify it works correctly because in general, professional programmers 1 to 3 lines per 100 lines of code after it is done. Now, what a lot of you identified is, oh yeah, it filled the 101st place of that array. But you didn't think about the consequences of what was the 101st place. And testers shouldn't try to the program works. Again, the purpose of testing is to find as many problems as possible. And as many problems as possible means that there are a few certain common things that happen as well. Because there is something called the Pareto principle, which says the vital few, the trivial many, bugs are uneven in frequency. If you have a subroutine or a function that has a couple of bugs, 4, 5, chances are really good there's a lot more than 4 and 5 in that particular module, because typically when somebody does design, they're doing an entire block of code at one time, and if they have a few errors in there, there's pretty much an underlying reason why. They didn't understand what they were doing, they were tired, they were careless, it's an inexperienced developer. So I often saw examples of this. I remember one project at IBM, there was a relatively new developer who we found lots and lots and lots of errors in her code. Lots and lots and lots of errors in her code. And the reason is because she was working on a topic, serial communications, which was brand new to her. This was in 1985, so it was when a lot of people didn't do that. And actually, when they rewrote the entire module, a lot of our problems and bugs went away. So, number one, you should be developing your test plan and you're planning, at about the same time you're developing your low-level design. When you are designing your test cases, you need to identify how you're going to work with inputs and outputs, internal designs, testing during design. In other words, if that example that I showed you a few minutes ago, if that was the code that you were going to test, does it really matter what the input might have been for that particular test? Maybe not. Next is when you do coding and documentation, it is good practice to interleave the documentation and testing with coding. In other words, document as you test, or document as you program. Now, and also test the function as you build it. And that's more what's called unit test. And I've talked a little bit about black box testing and white box testing already, right? And we're going to look at this in a little bit more detail. And then once something is released, there's going to have to be enhancement and correction of other bugs. So if you think about all of the software work done after release, 42% of it is user-requested enhancements. I have talked about in the development process something like agile type of methodologies, right? You give it a little bit at a time. Ooh, donuts. Oh, and that's from our photographer yet. Oh, that's even better. In Agile, you let your developer or you let your customer see it again and again and again. Adapting the program to work with new hardware. In other words, there might be an upgrade in the system. Fixing bugs, 25%. Documentation, performance. So incremental as opposed to big bang testing. You don't throw it all in one place and then try and test everything at one time. So we have something called a driver and a stub. And so if we had an example of this code. In fact, let's take a good example of this code that I just gave you. Oops, I'm hitting the wrong button. So let's say this wasn't main. Let's say this was, let's leave that as void. Void, fill it, void. And the whole objective of this is to fill certain types of oh, in fact, what is this? Is this global or local? Global, right? And so if we were to write a test harness for this, perhaps we would have our regular, in fact, let's think about this. How would we test this and then interrogate something, right? So how would you want to identify that you're going to run that function and then you're going to look to see what the results of that function would be? I want you to turn to your neighbor and figure that out, and then one of you is going to write it up on the board. And I'm going to choose you randomly, so you better work on it carefully. And so we are back, and I had a lot of people say, I don't know what to look for. So let's look at a good example. Remember, I've now changed this into a function that you can call somewhere else. So if I have my my main By the way, I did have a question. Remember, this void over here means that this function is not returning anything. This void over here means I'm not passing anything to the function. Not sure if everybody understood this. And so somewhere in here, I would say something like fillet. I'm executing it, right? Oh, yeah, I got to do. Because I'm not passing anything into it. And then I would, wow, I could do something really easy, right? I could say printf values no, and I should probably do a /n so it does it. All right, so let's take a look at what I just put here. That being, I'm wondering if the TV can even see this over here. I think they can, right? Just barely. So all I've said is run the function, and then I'm going to check the first value in the array and the last value in the array. Another thing I could also do is I could do a printf of I. Because a printf of I would be, what would the value of printf I be? So let's say printf I is equal to all right, so there we go. That could be a good test fixture. We're running it, and then we're interrogating the values. You could just as well pause the program right there and interrogate it. Now, what's the problem with respect to this versus the code that we have?
So it won't come out of fillet, right?
Yeah, I'll never run this line or that line or that line, right? It'll be an infinite loop. But here's the neat thing. What does that tell me then? That there's something wrong with the entire function and I need to take a look at it. That I'd run the test harness and I can't even do that. Oh, so I look at this and I say, all right, now I run it. I took away the equal sign. Will it finish?
Yes.
All right. What will it print out? Values 0 equals 1, right? Values 99 equals 1. And then, of course, this up here will be 100. And that's the type of thing you could do for a test harness. In other words, you're taking a look at what you are. You're just testing that individual function. And in fact, that individual function is going to be fairly portable. You can just put it in its own little project. And with this, you're able to test just that into great detail. Now, this is a silly little example because this is relatively small program. Relatively small function. But there are other situations where you would need to do the same type of concept with a whole bunch of different functions or a lot of functionality inside of one function. So let's go back to our slides. why we test incrementally and use these? By the way, that was a driver. That was not a test harness. A test harness is actually being able to do some automated testing. And so, I'm sorry, that was a driver, not a test harness. Why is it easier? As we said with BB, Big Bang, no function has been thoroughly tested. Most probably have bugs, and you have no idea now which bug in the module is causing it to fail. Less finger pointing, better automation, etc. Now, here is another example of how you can do the testing incrementally. Each one of these round circular modules here represents a software function, and you can identify the functionality fairly concisely. And I know you can see this really well, right? The objective is that each one of these nodes represents code, and each one of these boxes represents a test on that code. So this code is written, and then it is tested. This code is written, and you will need to test it, but to test it, you will need to introduce this code along with this new code that you just wrote. Now, this code up here should have been thoroughly tested here. So when you're combining this tested code with this untested code, you are fairly certain that if there is a problem, it is likely in this code. Along the same lines of, if this is a module and this is a module, you need to test because both of these software modules are needed. And if there's a problem, well, you pretty much can limit it to this module or this module. Once you have these two completed and tested, then you can combine all four of these modules together and do an additional test. And that's another way then of not only testing what's inside the module, but also testing interactions between the modules. That might occur that will occur because the nature of code is that things just don't run independently from each other, right? You usually have to pass data between software files or modules that you are using to develop. Now, in an example of what we did at Ericsson, one of my projects had over 1,000 different modules. And so very often, if you made a change to one of those modules, you would run it through a test driver very similar to what I showed you here and verify that it was okay before you checked it into the rest of the code base, because you want to verify that anything you change is not going to greatly or will not negatively impact the rest of the code. So notice that this is a lot of testing, but there is a lot of developing and testing and then ensuring that when you combine different modules that they all work together correctly. So I did the big picture. Now it's how to test and some characteristics associated with testing. What is extremely useful when you are developing code, doing unit test, and then later doing integration and then system test is that you should create a tracking database of bugs. And so when you have this tracking database, you write individual bug reports which identify where the problem was, things like what's the version of the software that you developed, version 1, version 2, 1.1, 1.1.2, 1.1.3, etc. The date of the discovery, usually the system automatically gives it a number. And then information about, what was the type of coding error? And this may have to be input later. Severity, can you reproduce it? Suggested fix, and then summary. Now, this is where I have an example of Erickson and how some people, this is really bad practice. I mean, I don't know if I've discussed this yet, but we had a test organization and a development organization, and somebody from the test development or the test organization found a bug, and they filled out their bug report. And then the bug report would be analyzed by the manager, and the manager would assign it to a code developer who likely that would be their area of code, and they would need to check and verify that this was an actual bug, and if it was, then to fix it. So the bug report was written. The developer responded inside the bug report, one of the response fields, saying, I can't reproduce this. This is not a bug. And then the testing person wrote into this bug report, yes, here it is. Here's some additional information on how to do it, how to find the bug. And then the developer responded inside the bug report, in one of the fields, saying, yeah, I still can't reproduce it. I followed this. And it was at that point, by the way, by that time, 1 week had passed, that the test manager grabbed the test developer by the scruff of the neck and the developer by the scruff of the neck, who were sitting in offices right next to each other, and said, both of you sit down at the same computer and figure this out in the next hour. And that's one of the problems associated with these environments, is a bug report is there for tracking, and you don't have to rely solely on that to get anything done, because you can easily walk over to the next office and say, I can't find this bug, can you show me? But here's one thing about this bug report and the tracking database is that, remember how I said Pareto principle? If a lot of bugs happen in the same module, this allows us to find out if there's a module that has a lot of problems. And so that's why it's important to mark every bug. A bug doesn't mean that you're bad or you're a bad developer or something like that. It's used to help the product. It's not personal. And in fact, people who test, it's not personal. However, most developers have the attitude of nobody wants to be told that their child is ugly. And the code is just an extension of themselves, when in fact the code is just that. It's an inanimate object that they worked on. So you have to make sure that you separate yourself from the product. In the same way, if you are a tester, you do need to understand that some people consider it an extension of themselves and might take offense. For example, I shared an office with one test developer or one tester who had this uncanny ability to piss off everybody whose code he was testing, because he would use such adjectives like stupid bug or idiot programmer or stuff like that. And just like nobody wants to be told that their child is ugly, nobody wants to be insulted either. And so just remember, you have to remove yourself from the personal ownership of everything, and it is a corporate problem. You need to get something done. Now, we've talked earlier about clear box, white box testing, where if you know how things are working inside the code, you can create testing situations to, for example, test if a loop is going to go on or if a condition will be met inside. Now, keeping in mind that this is one example of a test condition, right? By the way, I would be very sad if you had a variable called n in there, in your code. Now, if you're doing loops, sometimes we say that I and j is fine, But if you have any variables inside of your code, it had better be something more meaningful than just n. On the other hand, black box testing is a complement to white box testing, typically done more at the end of a project where you are executing typical type of operation and then maybe the bounds of those operations. And a good example I give on exercising bounds would be, for example, if I have a function that is supposed to, you pass into it a temperature in Celsius, and you want to pass out a temperature in Fahrenheit, then you had better make sure that you exercise values that would be appropriate for inputs and verify that the outputs would be good. In fact, this would be a really good example right now. Oh, and then comparing clear box versus black box, we're going to do an example right after this. Know what is inside the box so we can test to find internal components misbehaving and look at a large number of possible paths through which the program makes it. Impossible to test every path. So let's take a look at, well, this is a test harness. I think I showed this earlier. I think I'm just going to go on and not do that. But I'm going to actually stop right here, and I'm going to add to this another slide, and I'm going to ask you to do an exercise for me. So let's say I have a function. And I'm going to call it C to F, Celsius to Fahrenheit, right? And the way it works, input a valid integer Celsius temperature, or a valid integer Celsius temperature. Output will be a valid Fahrenheit temperature. Too bad I can't spell, I think. H.
There is no G.
Oh, okay. Oh, Fahrenheit. There we go. Yeah, I don't know how to spell. So, this is how it works. So I didn't give you what your assignment is. Write a driver to test the function using black box testing. In other words, you don't know how it works inside. So your goal is to write how it's going to work. All right? So by the way, the call would be obviously int C2F int, or that would be the prototype. All right, does that look good? I can't hear you.
Particle temperature is an integer or floating?
Int. We're working in an embedded system. So, obviously, sometimes float would be really nice, but do I have a float here? Int. All right, go to it. All right, so write a driver, test the function using black box testing. So, void main. I'm going to grab one of your solutions. I'm going to go all the way in the back to the people who hide. I want your solution. You just give it the whole book. Oh, you're going to hand it? All right. It's a little bit tough. Not quite. Anybody else? All right, here we go. Let me see. Just give me your whole binder. By the way, I didn't ask you to write the code. I want you to run it. Okay. Yeah, not quite what I'm looking for. So let me just show you what I would say, right? So what are you doing, right? You're just trying to test a couple of numbers. So not having known anything of what's going on, maybe I would say printf, let's see, input d, output d, and what's a good number? What's absolute zero? 273. Oh, negative 273. And then C2F, negative 273. Does that make sense? The answer is yes, that makes sense, or no, that doesn't make sense. All right. You like that? All right, so we can, so when you're doing testing, you always want to test a few of the boundary conditions. So what would be a good boundary condition? Correct? So what would you expect to happen? Maybe some error or something like that, right? So again, testing boundary situations, let me do it in order. Wow, look at how far that went. I have no idea why the heck that ended up there. What the heck is going on here? It's a bug? Copy. Paste. We're just going to wipe that out because that's just ugly. So 74. And just for grins, I think I'm going to put another one up here that might be a lot bigger down there, so maybe 30,000. And then obviously a good one. I like nice examples that I could come out with. So what's going to be the answer to this one? Yeah, minus 40 is the same in Celsius as it is in Fahrenheit. So, and then maybe something big like 10,000, right? All right, do you think that's good enough? What about what? What about what?
So approximate values,
What about what?
the common values that we come across every day.
Oh, you want to do a common one? Okay, we'll do 23. 23 is about 68, right? All right, so this is just an example, right? A couple of values. Now, there is one problem though. It'd be nice to know what the function is inside, right? Because maybe if you had some insight as to what the function or how it ran, you might be able to do something, different and improve. Well, it turns out that this is the function. What in the heck? Why did I put this in there? Well, as it turns out, if your input is higher than this, your calculation here will result in bigger than an integer. And so the designer who was smart did that. Well, let's put it this way. If the programmer for this were poor, they would not have done, they would not have done this line or this line in their software. And then they would have all sorts of problems, which we'll continue in the next class. Thank you very much. All right. Just as a recap, we had a class exercise, write a black box driver testing, or write the driver to test the function using black box testing. I offered, by the way, using the function C2F and input a valid integer Celsius number. And so the result that we came up with that would be this: somewhere really negative, somewhere about near absolute zero, somewhere in the middle, somewhere high, and actually we had another example. But then I said, well, this is the function. For example, there's really no use to try and find a temperature less negative than absolute zero because it doesn't exist, right? Theoretically, it doesn't exist. And so to do that, then we set the minimum of the temperatures for your input is negative 273. And by the way, if we have something too cold, then we'll just return a really, we have to return something, right? Returning a 0 would not be good because that's a valid answer. This is not a valid answer, so that would be the appropriate thing to return. So you know that if you get something really, really low, then that's not a valid thing to ask for. Also, the other thing to consider, and I mentioned this in the last tape, that if you have a Celsius temperature which is greater than 18185, you won't be able to represent that as a integer, 16-bit integer, which is what we're working with. And so if you have anything greater than that, then you need to return something to say you went out of the range. And then, of course, you could just return the actual computation, keeping in mind that it's always better to multiply first than divide. In fact, is this a problem? So this is going to be a problem because temp in is an int, and if I multiply by 9, I will be out of the range. So it's especially helpful to test something near this number because this multiply by 9 would go way out of its range, right? So maybe if I did my white box testing, and as I said, write the driver to test the function using white box testing, with this code itself, I would actually have an error. And which line would give me the error? It would be this one right here, right? This would turn out to be, oh, no, it's something a lot different because it tried to do the multiplication. It went way out of the range of multiplication would be allowed. So what I want you to do is the following. All right. So this is, by the way, the solution for white box testing. What I want you to do is to identify how can you change this code right here. Well, I'll let you just turn to your neighbor. You know, do you do division first? Do you do multiplication? Do you change the, do you cast it? Which is best to do? In other words, go ahead and do the calculation yourself. Do it both ways. Do the division first, then the multiplication, and do the casting. All right, so since everybody said they were done, I'm going to walk around and I'm going to ask you to write some solutions on the board. So you write your solution on the board there. You go ahead and write your solution on the board up there. Yeah, find chalk wherever you can find it. Solution up on the board. And if you need chalk, it looks like there's a box up front. And you go ahead and write your solution up there. And you go ahead and write your solution there. And could you write your solution up there? And it looks like there's enough chalk around. Maybe I need to get some from the front. And no fair looking at anybody else's solution. Oh, jeez, look at that. A box of nibbles. Obviously, somebody doesn't like to throw away chalk, so no piece of chalk in here is bigger than 1 centimeter. Oh, no. Just I'm sorry. Just do the calculation line. Yeah, you don't have to do anything else. Okay? Now, here's what I want you to do. I'm going to give you the value of 15,000. So, solve your code with the number 15,000 every step of the way. So in this first one, temp in 15,000 divided by 5 would be 3,000, right? Oh, no, every step of the way. I want to see you do every step. Oh, I'm sorry. Don't use 15,000. Use 15,003. 15,003. Ding. Correct. So start with 15,003. So 15,003 divided by 3 is, nope, it's an integer. You can't have any decimals, right? All right, so let's take a look. So here we go, right up here, 15,000. This is a good example of this, right? 15,003 divided by 5 first, you got 3,000. Multiplied by 9, you got 27,000. Add 37, you have 27,032. How close is that? 27,037 is what he should have got, right? So you're out by 5. Wow. All right, let's look at another example over here. Oh, this is even worse. All right, first of all, this person said 1.8, but this is integer, right? So it turns out to be 1. So now it's really going to be 15,000 times 1 plus 32, 15,003. There we go. So the answer is going to be 15,035, way off from 27,000, right? Way off. Same thing over here. Oh, man. I hope we have better luck over here. Okay, temp in 5 times 9 plus 32, 27, 32, yeah. Let's see, what else do we have over here? Yeah, this will be right here. This will be an error. So let's see, what is 15,003? Oh, I can go this way. No, I'm on the wrong thing. I got a calculator that'll do this. And it's really important to understand this. So my 15,003, and I'm going to multiply it by 5. 9. And my answer is going to be 0F73. There'll be a 2 up here, but that's not in the range, right? So obviously that's not going to work. And let's see. Oops. So what is 0F73 is actually 39,055 plus. Oh, we get to divide by 5 now. 791? And then you divide it by 5, and that's 791, and you add 32. So now you're at 823. Wow. How close is that? And then we have over here, that's not even code. Oh, come on. All right. So, have I made my point? All right, now here's the question. Would testing have found this? Would white box testing have found this? Yes. All right. So, the answer to this, if you're not allowed to use float, would be what? Well, I said you're not allowed to use float. Who says I can't use long? So, voila. Oh, and then all the way at the end, I cast it back to an int. What do you think? Do I have the right number? 1, 2, 3, 4. 1, 2, 3, 4. Yes. So here's the neat thing. Would testing have found the bug? Yeah. Right? If we had thought we fixed it like that, would testing have found the bug? Are you sure? Yeah, it would have found it, right? If we had implemented that, would testing have found the bug? Yes. Oh man, we would have found more than one bug, by the way. All right? No, that's the same one. That one over there, yeah, we would have found more bugs in this, right? And that one over there wouldn't have compiled in the first place. And where's my other one over here? Oh yeah, that one. Would you have found that bug too? So in the end, really, how many bugs were there in this code? Just one, right? And there were a couple of different ways that people... Actually, isn't this interesting? I think there's only one, this is the same one. That was different. That was different. That one have compiled, and that was different over there, right? So in the end, there's two things I want to point out here. One is when you are writing code, you have to be very cognizant of the size of the data that you intend to work with, and not only the size of the data, the type of the data. Meaning float versus integer versus long integer. This would have been simple with float. But maybe you have only 8K in your very small microcontroller, very similar to for program, like you did with the TI MSP 430. And you just don't have the space to put in the software functions that will do floating point computation. Of course, if you have the Renaissance RX63N, you have a floating point unit in it, that wouldn't have made any difference whatsoever. So in that case, actually, the function would have been a lot different if it were floating point. Because not only would I have negative 27 or negative 273, it would be negative 273.15 or whatever absolute zero is. And I doubt very seriously I would even need a maximum temperature. Well, not anything I would really care about. Because I think the temperature that would have shown up going out of range would be, first of all, impossible. So, all right, you get the concept, the point? Got it? Good. Let's move on. So does that make everybody scared? You never know when something like this will show up on the test, which I'll hand out at the end. All right, so when you're doing testing, there is a great need to actually plan out what you're going to do. So I don't necessarily just write this code first. I actually will write a plan of what I intend on doing. So when I mean this code, I mean the test driver. I actually say what my objectives are for this test. And usually a test plan is for all of the code, not just one individual function. Now, in the test plan, you're going to say what your list of test cases are, what is success, what people you need, how you're going to do regression testing. In other words, go back and retest those parts of the code that failed the first time when you tested it. And also you have to identify hardware and test environments that you're going to do this under anyhow. A good example. Let's say I have and this is historic, an Ericsson mobile phone. Just pretend, all right? And my goal is to test functionality associated with this phone, but mostly in a black box testing environment. I would say this is going to be a black box test. This is what I'm going to do. I'm going to require that I press certain keys on my mobile phone and expect this type of result from that test. Now, it could be keys. It could also be stuffing in or attaching to an external antenna to this a special test box that replicates what goes on in a wireless network. In other words, have the phone run and then replicate or make it appear as if a phone call is made from out there in the world destined for this phone. How does it answer the phone? And then you have to hit a button to make sure that the thing is answered. Other types of events that might occur. So you have to identify, oh yeah, I need the RayCal test box, which will attach to the antenna of my phone, which will create incoming calls and accept outgoing calls. And then you would list a whole bunch of test cases. Now a test case is a specific procedure that is going to test a particular requirement. So a requirement might be you shall be able to type in 11 digits for a phone number, 1 plus the area code plus the actual number, and have that phone make a call. You shall be able, that'll be one requirement. You would write a test that would specifically do that. Another one might be you shall be able to type in a 10-digit number, 3-digit area code, 7-digit number, to be able to make a call. And you would do a test case for that and verify. And you would, in your test case, you might make a couple of calls as a part of that. So you would identify the specific requirement that you're testing, would identify success and failure, and the specific tests that you intend on doing. Type in an 11-digit number, hit the dial button. Type in a 10-digit number, hit the dial button. Those are the different types of test cases you would have, and those test cases, as I said, would be identified within your test plan. Here's an example. Let's say we're doing lab number 4, requirement 7. And the specific passing is that all characters are typed in on the are displayed on the LCD and hyperterm window. So what you have is a PC connected to your Renesas board. The PC will run the application called hyperterm. You will then type characters on the keypad, which will be sent directly to the RX63N board, and then will be echoed back to the hyperterm terminal and will show up on your terminal. So you're going to, in this case, type the A key on the PC. Ensure it is displayed on the, I should put the RYDK board, LCD, and on the PC hyperterm window as well. And then I'm going to test the characters, character turn A, capital A, lowercase, Z capital, Z lowercase, asterisk backslash 09. Why did I choose those? No, they're ASCII characters, right? But do I have to do A and B and C and D and E? No. So I chose one at one boundary, upper and lowercase, one at the other boundary, a couple of special characters, and then the range of numbers. And this would be an example of a test case that I am testing requirement 7 in my lab exercise. So a good test has a high probability of finding an error. So let's look back at our temperature example. The test, boundaries of those selections. I would find if there were an error, like if I put the wrong number in for that boundary condition, right? Like maybe it's really 1/8. You know, I didn't really do my math correctly, did I? Or did I? Maybe the number is really not 18185. Maybe it's really 18184. You never know. Maybe I did the wrong number. So a good test would find that error too, because I'm testing the boundaries. A good test is also not redundant. So you noticed in the test driver, I didn't do too many of the numbers inside of the boundary. I just did one, because any more than that would be redundant. Best of breed, meaning that it has the highest likelihood of finding a class of errors. And it turns out that my test harness would have found the one error I had in there. Neither too simple or complex, and should test rarely used as well as common code. So a rarely used example would be if I had a really low temperature. Because technically I should not really input a really low temperature. Because if this were maybe a temperature sensing embedded system, right? For all intents and purposes, I really wouldn't expect to be measuring absolute zero anyhow, but I put it in there just in case. I'm going to skip this one. I think I've already talked about this anyhow. Now, when you are testing, typically what you do is you get an entire version of code. In other words, let's say for our mobile phone again, I will get one version loaded on the phone, and now this device I will use to test. Now, if I find an error running a test case, I don't immediately go to the programmer and say, can you fix this error and give me a brand new version of code so that I will now start now and test this version of code? No, usually what you do is you test a whole bunch of test cases. You test as much as you can. You find all the errors. You report them. The development organization will then fix as many of those as possible. They may find out that, this test is too rigorous, or I will never find this situation again. And so they won't try and look for the solution or try and solve it. But then I will get a brand new version of code, and that brand new version of code should fix all the problems that I found that the development organization said they would fix. So here's the question. Do I run all of my test cases again? Or do I just run those test cases that failed? Oh, okay. Who votes all? All right. Who votes just those that failed? Who votes just those that failed and a nice representation of all of them? And that's when I raise my hand, all right? So the answer is, when you release your version of code, the very last version of code that you release, you should test everything again. But when you're doing interim versions, testing takes a lot of time. For our mobile phones, it would usually take 2 weeks to run through every single test case. That's a lot of time. When in fact, usually if one test case ran correct the first time on the first version of code and ran correctly the second time on the second version of code, it's a good sign that it's going to run and pass every single time. So I don't have to run it again and again and again and again. But I probably want to do that all the way at the end to make sure nobody broke anything. On the other hand, any test case that I ran that came up with an error at any time, I probably want to run every single time I test the code. Every single version I get to test the code. Because even though they fixed it, they may lose the fix. And I've seen it happen where somehow a fix was made, it was put in a version of code, and then in the next version of code it reverted back to the original version of the code. What happened? Oh, I don't know. Maybe somebody overwrote it. So it's always good to retest anything that had failed in the past. And that could be your representation of other test cases that you run every single time. All right? So lots of randomly generated data you could use as your input. Customer reported bugs, you always test those as well. So, how easily can a program be tested? This is some nice information that you can read on your own. You never know when it might show up on an exam. Controllability, simplicity, understandability. Just go ahead and read this. This is good to take a look at, all right? Any questions before we finish up this module on testing? All right, thank you very much.